So yeah, this looks like a good one right here. So we'll do this in a couple of different ways. We'll do it the stack key way, and then we'll do it the, so my question number one is going to be similar to yours, except you're going to get a different set of temperatures here. And then we'll do it the flowchart way in just a second. So first thing I'm going to do is just I'm going to highlight these, and I'm told down here I want to find a 98% confidence interval. Up here it says you must estimate the mean temperature in degrees Fahrenheit from the following samples. Okay, so we have the temperatures of something, and we want to say, okay, well, what's going to be the average temperature for this whatever we're measuring. Stat key. Oh, I had a link to it right there. And confidence interval for a mean, right? We're definitely doing a mean here. Make sure we're on the right page. And edit data, and hopefully I copied that correctly, and it will just paste in there. Didn't copy it correctly. Try that again. And you want to be careful not to copy too much on the web page, otherwise it'll paste in funky. That looks okay. Notice I do not have a header, so you got to pay attention to these, otherwise you get the wrong values. It miscalculates. And it says I have 12, double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. And so then the member confidence intervals, we did this 3 weeks ago. We get the data in there, and then we just hit generate, generate, generate. And we want at least 6,000 samples. So again, what StatKey is doing here is creating what's called a sampling distribution. And a sampling distribution means take this sample here, make a deck of cards, and then give me 7,000 more samples of size 12 based on that deck of cards. And everyone's going to be a little bit different. Like these cards over here got drawn more often than these cards down here. So I have a mean that's in the higher end. But it could be the lower cards got drawn more, so I get a mean in the lower end. But notice that this does have that bell shape, which is kind of remarkable that we always get this bell shape. We're doing a confidence interval, which is always two-tailed, and then we have to get the right confidence level in the middle. 98% for mine. Double check what yours is. So 0.98 as a decimal. And then it gives me this down here. So let's put this in my spreadsheet. New page, please. And screenshot it. And all I really care about is the graph and the numbers at the bottom. And then I'm going to redraw this, add to current page. All right. Let's put you up higher and just a tiny bit smaller so I can fit my drawing in. So what am I measuring here? Temperatures. And they look like degrees Fahrenheit to me. Oops. Did it say in the problem? Yep, Fahrenheit. In degrees Fahrenheit, and we are trying to estimate the mean. So here's our point estimate. So we think that based on this X bar, we think that's approximately the population mean, according to the central limit there, and they should be about the same. And we believe that's 49.511 degrees Fahrenheit. Now, the other thing is we can never be sure that's the population mean. It could be any number in here, and actually it could be outside. I'm never 100% sure. So we have an so this again is a point estimate right here. Some review of terminology. We also can make an interval estimate. So our interval estimate is going to be a low of 43.429 and a high of 55.600. So we're 98% confident that the average temperature of this scenario is somewhere between 43 degrees and 56-ish degrees. And then we can also find the margin of error. So let's do that. And the recommended way to find the margin of error from stat key, so let's put that over here, I guess. So the error bound on the mean is to subtract these numbers, or sorry, yeah, subtract them, right? Find the distance and then divide by 2. So what is 55.6 minus 43.429? And then cut it in half, right? So we take the whole width and we find half of it, which is similar to taking the upper number minus the middle or the middle number minus the lower, but because of this is a simulation, it's not perfectly symmetric. So this is the safer way to do it. So 43.429 calculator time. So parentheses 55.6 minus 43.429. Double check I typed those right. Yep. And then divide by 2. So close parentheses, divide by 2, and blow that up. So there's my calculation, 55.6 minus 43.429, cut it in half. So I have a margin of error of 6.0855. So I could also say we believe that the average temperature is 49.511 plus or minus the 6 degrees. So we're within 6 degrees of 49. Okay, so a couple of ways I could state that. But first I want to draw my version of this just for practice. And you should always draw one of these on your paper when you're doing these problems. So in the middle goes the point estimate, the 49.511. And then we mark off our edges, 43.429. That's my lower estimate, and my upper 55.6. And then I'm going to make a note of the margin of error here. So that's X bar. And the error bound on the mean, which I could have drawn on this side too, it should be the same, is that 6.0855. And I should also write in here that this was a 98% confidence interval, and I could throw the tail probabilities in here too. And again, this would be my estimate, oops. Of the average temperature. Just to be clear on a couple of things, I think the average value of any possible temperature for this situation is somewhere between 43.4 and 55.6 is what we've calculated here. An individual temperature, like maybe these are daily temperatures in a particular month in some area, individual daily temperatures could be vastly outside of this interval. I'm looking at averages, and the range of an average is always going to be much smaller than the range of any individual number in the data set. So those are two different things, and they're easy to confuse. And when I've been grading the confidence intervals and hypothesis test, there's been lots of confusion on that, and I try to make a note to you when I think you might have confused those two ideas. But my point here is, again, look at these numbers right here. They're from the middle, they're 6 apart. But if we look at the original data sets, we can see there's a much wider range. Whoa, I didn't mean to hit that. Back here. So let's see. They don't give me a lot of summary statistics here. I can kind of look at it and guess. Oh, yeah, the picture kind of shows me. Yeah, so here I have a low of 35.9 and a high of 62. Okay, and again, compare those to my confidence interval, which is 43 to 55. So the range of individual numbers is always going to be vastly greater than the range for an average. Because remember, the average, what does it do? It sucks in the min and the max, and we forget about them. Okay, so it really compresses data when you do averages. So confidence interval is going to always be a tiny range compared to the range of all possible data values from individuals. All right, let's do this spreadsheet style. So let's go to my drive. And we're going to redo these problems with the formulas from that flow chart. I think I need a new sheet for this. Same stuff I'm going to do here works in Excel. So if you're whipping out Excel now, I highly recommend you play along. Okay, so inferential stats, overview, review. And this is problem number 1 from the applications. So I need this data. And notice this is a small data set. I'm doing a mean, so I can't use a normal distribution. I have to use a t-distribution according to my flow chart here. And I will post this flow chart. Where'd it go? Back a couple pages. Yeah, that flow chart right there. So if you didn't get that in your notes, then I will post this so everyone can get it. And I highly recommend you redraw it instead of printing mine. So we have temperatures in Fahrenheit. Get those, and you should label everything, very important. This is app 1 down there. All right, so a couple of notes here. I have a small sample, and I was given no information about the population standard deviation, so that is sigma, not known. And those pieces of information imply use t-dist, not the normal dist. And let me blow that up a little more. Hopefully that's readable. And let's see, I don't think I need that up there. Okay, so this is just some notes to me to figure out where I am in my flow of what I know about information in the inferential statistics. So I'm estimating a parameter, right? So they asked me to identify a parameter, and I'm doing a mean, and I don't know sigma, and the sample size is small. Okay, so I'm in this branch right here. So I'm going to have to apply this formula here, where I take a t-score times the sample standard deviation divided by the square root of sample size to get the margin of error. So let's build that. So known information. So we have the sample data next to us. I need to know the confidence level. So confidence level, and that was given to me as 98%, I believe was mine. Right away, you should draw your picture. So can I get a screenshot of my picture in here? Because that's going to help me figure this out. I guess not easily. Get back here, where'd you go? I'm going to start a new picture. So on a piece of paper, you should be sketching this out. And I'm taking not the stat key approach, but the spreadsheet approach. I'm just going to start over with my picture. So again, what am I trying to do? Estimate average temp mu. And drawing a rough normal. I need to figure out what is X bar, because that's going to be the center of my confidence interval. I am doing a confidence interval for this estimate. And I want to figure out what is the error bound on the proportion so I can get this upper number and this lower number over here, such that 98% of other samples like this one would be in the middle. What's the lower end of averages? What's the upper end? And this says, my formula from the flowchart says find the right t-score and then take the sample standard deviation, divide by the square root of n for that calculation. To find the t-score, I need to do a t-dist. So I need to get a t-value that goes with this lower number here. And to find a t-value based on a percentage, this 1% up here, I'm going to use what's called an inverse t. And I think, let's see, the Excel formula, I think is just inverse.t. Let's go double check, or the Google Sheets. So let's see, I need to know my tail probability, which we call alpha over 2. And so that would be equal to, I need to know what is the tail. So the tail would be 1 minus this percent up there. And then I want half of that. And I want that as a percentage. And I don't need any decimals. So back in my notebook, I know that the confidence level is 98%. Alpha is always 1 minus the confidence level. So that would be 1 minus 0.98, which is 0.02. And the tail probability here is always alpha over 2. So next I need to calculate alpha over 2. And I just did that in one shot in the spreadsheet. So what is this? 0.02 over 2. So altogether, we could say the formula for alpha over 2 is to take 1 minus the confidence level and then divide by 2. And on a calculator, that numerator is going to be in parentheses. And sometimes on my spreadsheet, I'll have both alpha calculated and alpha over 2, so I don't have to worry about parentheses. So just to do it that way for fun, we'll just call this alpha. Alpha is always 1 minus the confidence level. And whether you want to leave it as a percent or a decimal, that's up to you. And then I need the left or the right tail. They're both the same, so that's what we call alpha over 2. And you may remember seeing this in the book way back 3 weeks ago, equals this number over 2. Once I have that information, I also need information from the sample. And from the sample, I need to know what's the sample size, n, what's the mean of the sample, and what's the standard deviation of the sample. So let's get those numbers here. Let's highlight those. There's my highlighter right there. So just to double check, it's always a good idea to have the computer count, because I'm always miscounting things when I point to stuff and try to do it. Confirms there were 12, average of the data, and standard deviation. And I recommend the .s version. Okay. All right, so then for the sampling distribution, I need to calculate what we call the standard error, which is a standard deviation. And back to my flow chart. The flow chart says, that's this value right here. Let's highlight that. And then we have to calculate the t-score. All right, so the standard error here is going to be the sample standard deviation divided by the SQRT of the sample size there. And then I need to know the appropriate t-score. And I believe that's, let's see, t dot inverse. Okay, that's the one I want right there, I think. It's not giving me the description of it. There we go. Calculate the negative inverse one-tailed t-dist. Yes, that is what I want, one-tailed. So then it says, okay, what's your one-tail probability? So that was that alpha over 2 up here. And then it says, hey, what are your degrees of freedom? Degrees of freedom is always 1 less than the sample size. It's always n minus 1. I'll put this in the notes. So I want to go get that sample size and take away 1 from it. And that gives me my t-score, and it always gives me the -1. And the t-score is like a z-score, so let's put that in the notes. Next. Okay, so to calculate the t here, red, I'm going to use the t.inv formula. And the TINV wants to know what's that tail probability. So that's my alpha over 2 value. And then it wants to know what's the sample size minus 1. Okay. So in this case, I entered the calculation from, that was that 0.02 here. Oh no, oops, I didn't write it down. That one, alpha over 2. and then an 11. So all it needs to know is what's the sample size minus 1 and what's the tail probability here. And a t-score is like a z-score. The middle z-score is always 0. You haven't gone anywhere from the mean, and then it counts how many standard deviations are you down the line. So on this side, your t-score is always going to be a negative number, and on this side, the t-score with the upper is always going to be a positive number. Okay, and all I want is the positive version, even though it gives me the negative one. So we'll have to tweak that. So back here, so I'm just going to sneak into this formula right here, and I'm in between, or I guess out to the edge here, I could just multiply this by -1. No, I'm going to go in front of the equals and sneak it in. I'm going to say, give me the opposite of that. Okay, so I got that number here. That these are both about 2.7 is a coincidence. So then the error bound on the mean, in this case, is equal to the t-score times the standard error. And so altogether, that number right there is, let's see, the t-score times the sample standard deviation divided by the SQRT of the sample size. Separate that out a little bit to make it readable. So that's the calculation I just made right there. And to do that, I needed to know the sample data and the confidence level to figure that out. So notice this one is a little wider, 7.4 instead of the 6.1-ish that I got earlier. And the t-distribution kind of does that on purpose. Since we don't know the population spread, the t-distribution says, let's just make it a tiny bit wider because we don't know so much. Not only do we not know the mean, but we don't know the standard deviation of the population. So let's make our net a bit bigger. And that's the safer thing to do here. But you don't want to make it too big. So the t-distribution kind of splits the difference. It says, okay, let's look a little bit farther out for the population mean, but let's not go too far, otherwise we have a useless estimate. Once I have that, then I can get my interval, because notice I have some important things here. Let's use bold. We have the mean here, the center value, bold, and we have the margin of error here. And that gives me my interval. So I'm just going to round these numbers. Let's see, did the problem say where to round? Accurate to 1 decimal place. Now, normally I would say 2 decimal places because the data has 1, and usually with statistics we go 1 more. Let me read the fine print. Find a 98% confidence interval, accurate to 2 decimal places. I'm stating the reason there. Sorry, helps if I read the whole sentence. Yeah, 2 decimal places. Usually with statistics, we go 1 more than the data. Data had 1, we state 2. All right, so back here, so I'm gonna report my mean as 49.56. So let's get that in the notes. There we go. So I'm just gonna redraw that picture there. .56 is my center, and I now have a margin of error, which is what, 7.45. So this is my X bar and my error bound on the mean, 7.45. So then I can add the 7.5 to this side to get the upper, and I can subtract the 7.45 to get the lower over there. That's the last thing we do on the spreadsheet. So lower and upper equals the mean minus the margin of error, and then equals the mean plus the margin of error. And so what do I get? 42.11, 57.01. I get that right in my head again. 42.57, okay. .11, 57.01. So that's my confidence interval. So then I'd write my sentence. I'm 98% confident that the average temperature is somewhere between 42.11 degrees Fahrenheit and 57.01. And this problem should take either, now notice that's a slightly different answer than I had from StatKey, but they're in the ballpark of each other. 43 to 56-ish, and 42 to 57-ish. So the t distribution always goes just a little bit wider to accommodate the fact that we do not know the standard deviation of the population. Okay. Sorry, homeschool interruption. Yes, dear. Okay, sounds good. And this is the last week of public school, so I don't know about any of your households, but we are frantically trying to get our kids to get the last of their work done this week so they can survive school. Very exciting. I had a ton of teenagers here last night asking lots of math questions and grammar. I'm not very good at English grammar. All right, so let's enter my number. I'm going to go with the central limit theorem version of this right here, which was the 40. Oh, yours was last week, Brenda-Lee? Okay, thanks. That's very exciting here. It's going to be a wild week. 42, I think it was 42.11 central limit theorem version and 57.01 if I remember right. Wish me luck. Yay, I got it right. Woohoo.